So can everybody hear me well? Excellent. So warm welcome to everybody. Just let me know if the audio is okay, so that in the back you have no problems hearing. So a great welcome. And what I wanted to do now is to give you some introductions to where you find the teaching material, schedules, practicalities, etc., etc. So you probably have tons of questions. So we will go slowly through many of the things the first hour. And then the next hour, we are going to begin with what we normally call a low-level machine learning method, which is called linear regression, which probably many of you have seen when you took a course in linear algebra. So I'm the guy with this kind of, in Norwegian, a little bit funny name, but just call me Morten. I mean, that's good enough. And we are going to have our lectures here for the rest of the semester. And then we are going to have lab sessions on Tuesdays and Wednesdays. And these lab sessions are perhaps the most important part of the course. All lectures are recorded, so you can always look them up afterwards in case you missed something or you want to revisit it, or if you cannot be here physically. So you can also attend via Zoom, and you can see that we have 2 people via Zoom now. So this is also fully possible. There is no compulsory thing in this course except for the 3 projects you have to hand in. That's the only thing. And that means that you, if you do have a part-time job, but it doesn't fit, or if you have other obligations, then you can always revisit the videos or just join via Zoom. Okay? So this is a little bit about some of the practicalities. Is my English okay? So not being a native English speaker, it means I do have an accent, obviously. So let's just look at some of the information which you probably have seen already. So this is the official website of the University of Oslo. And the code has is a cloned course, which means that it's a course offered both at the master level and the bachelor level. But we do also have people from other departments who can take this as part of their PhD. So we will be a very, very heterogeneous group because we have people from the whole College of Natural Sciences, or Matnat-fakultetet, as it's called in Norwegian. We have typically people from social sciences, humanities, medicine, and so on. So it means that in the beginning, there will be some elements of basic repetitions. So I hope you don't get offended if you find the level too simple, because then you can always do something else. You can go ahead with other types of exercises and or perhaps do other things. So this is the official website, and as you know, you can click on this one, and if you are not fully familiar with that, you can actually, if you look at, let's say, the lecture plan here, you can subscribe to these activities. So Physics 3155, since this is a bachelor course, you would have to click, it comes up automatically. You can see this is not available in English. So if you go to the master degree level course, so this is some rules which a university have established. If you go to that one and you go to the same, you go to the schedule and you see an English here, you will see that the site is in English. Now, the schedule which you find here, if this is the first semester at the University of Oslo and you go on schedule, you can actually subscribe to these activities if you just click on this link. I guess most of you who've been here have seen that before. So that means that you will get typically an email in case of changes or updates. And that can be pretty handy. I think you can also set up for receiving everything through an SMS. So how many of you are using this option? Not so many. This is actually a nice option. So this is the official website, and you will find a lot of the information here. And you will find things like Canvas, which we are using, messages, which I put in on a weekly basis. And you will find typically here the same message, which you found in Canvas. So we're using Canvas as a way to communicate. If there is an interest, we can also set up a Discord channel for discussions of exercises, projects, and so on. So just let me know. Now, another thing which I recommend doing in the very beginning here, so there is a link to a form where, in case you don't have partners here, because we typically recommend for the projects and exercises to team up 2 to 3 people and collaborate. And this is often very beneficial because, I mean, one of you may be a wizard in mathematics, the other one may be pretty good at, let's say, the specific algorithms or programming. And then you have people like me who are masters in making coffee and cracking lame jokes. You always need some people like that in a group, right? Just to waste your time. I'm an expert at that. Okay, so this is very much up to you, but typically teams of 2 to 3 people, that works pretty well. And it's very beneficial because you often learn from each other. Now, many of you come from different departments, which means that you probably don't know so many people here. So in case you wish to, if you fill in that form, we can try to team up people. And what I've typically done every year, because there are some roughly 30, 40 people often who want to do that, then I try to put people together according to interest, so that we don't put together, let's say, 3 bioscientists, but we put together, let's say, a mathematician, a computer scientist, and a bioscientist, so that they can, in a way, learn from each other. But if you already have decided for somebody you want to work with, I mean, then it's fine. You don't need to fill in that form. So try to do this as soon as possible, not later by the end of next week, because I would like to set up the groups for the final project. Okay? Anything unclear? Yeah? So in principle, there should be a difference, right? I don't set a difference. It's exactly the same. So the university actually got acceptance for having these clone courses some 20 years ago, because there were many courses which were typically at the interface between the end of the bachelor degree and the beginning of the master degree. And for many people, it was not possible to fill in their bachelor degree with all the courses they wanted. So that means that we made this kind of clone courses, which in a way represents a course which is at the transition between 2 degrees. So in principle, the government or the, let's say, the Ministry of Education wants us to make a distinction, but I am a notoriously lazy guy, so I haven't done that. So it means that the project will be exactly the same. Okay? So this was a little bit about finding teammates. If you go back to this one, you will find down here the link to the teaching material. So if you want to go to the teaching material, there is a GitHub site. So how many of you have never used version control like Git and repositories, or repositories like GitLab, GitHub? Okay. So we will actually get an introduction to that at the labs tomorrow and on Wednesday. But Git is a version control software, which is fantastic. It's actually one of the best ones. And it acts on ASCII files. So it stores the differences between text at different versions of your file. And then it reconstructs by looking at the differences. So it doesn't store the whole file, but it stores the differences, the changes you made at a given time. And then you can reconstruct your file at the moment, let's say 1 month ago, in case you made some changes to your program and it doesn't function anymore, but you know that it functioned 1 month ago. So having version control is something which makes life so much easier. Also, I had once a master student who was on a train, was writing on a master thesis, and went to the restroom, came back, and somebody had stolen the laptop. On the laptop, there was 3 months of master thesis writing, which were just lost because that person hadn't used version control. So version control is a very great way of backing up. And you as a student at the University of Oslo, you have free access to GitHub. and you have unlimited accessibility. So earlier, when you exceeded a certain file number, you had to pay, but this has been relaxed more and more. So essentially, GitHub is a very, very useful repository, and Git is a version control software. So most of you at University of Oslo, you've been used to this kind of software. And here you can find everything, which means also that I would typically recommend that you either fork the repository and you can use that as your teaching material. Alternatively, you can just take this one and clone it on your laptops. So what people do often is that they do a clone, because then you get the weekly updates, because I keep updating everything every week. Typically towards the weekend, I've made additions to the files, because there are typos, small errors, inconsistencies, which you guys spot, and that improves the quality of the teaching material. So there will be roughly a weekly update. So by using a Git pull at the end of the week or the beginning of the week, you will get the latest version. So we would also put projects, exercises on the GitHub site. Now, in the beginning, you may get a little bit confused and ask yourself, where is all the material? So one direct way of accessing it is by clicking on the Jupyter book. So if you click on this link, you will find essentially all the chapters we are going to cover. And then if you scroll down here, you will find the weekly material. So the slides of today is something you will find there, but you will also find the exercises for tomorrow and Wednesday. They are exactly the same sessions. Any questions so far? Everything crystal clear? Goody. I mean, don't hesitate to ask questions, guys, eh? So this is roughly the kind of layout where you will find teaching material. So these lecture notes are being updated continuously every year. I keep adding things to them, essentially because this is a field which changes swiftly. So 3-5 years ago in machine learning and AI is what we jokingly would call archaeological time, because the field is moving so fast. It means also that some of the things we are going to cover in the beginning are what we are going to call the pre-deep learning revolution methods, like random forests, which some of you may have heard of, support vector machines, linear regression, etc. These are methods which have been around, like linear regression, since Gauss invented it in the 1850s. So some of these have been used to fit data, but they are normally included in a machine learning course because they have a low level of mathematics. They are easy to understand because you actually have an algorithm which is very precise, and it tells you how you learn the parameters of a specific model. We are coming back to this. So they are typically included in a family of methods, but it's when you come to the deep learning methods that you have the new stuff and the interesting stuff. But we need to go through some basics, because you as a group, you're also going to be a pretty scattered group with different backgrounds. So some of you may have forgotten all linear algebra. So I was a kind of person who loved repetitions, because after the exams, I had typically forgotten everything. And then the next semester, the teachers would say, hey, you have seen this before. What? Never seen this. So repetition is something which is beneficial. And I hope you don't find that too boring. Also, I tend to repeat myself. That is what you call a professional damage. So my daughter always says, Dad, you don't need to explain things 2 times. I've heard it once, and then you don't need to repeat it. So if I keep repeating myself, it's often because that's a professional damage as a teacher. Okay. So this is where you find essentially the material. And if you click on this one, you will see that tomorrow, for those of you who are not familiar, we have a GitHub setup, setting up a GitHub repository. There are also Python environments and software, which we are going to recommend strongly. And Python is going to be the main programming language, but every year, we always have a fraction of people who want to use Julia, or even people who've been writing from scratch in C++ and Fortran. So this is up to you. And we can assist you in all these programs. But the standard default entry point in machine learning is Python as a programming language. But if you are familiar with Julia and you want to use that one, feel free to do so. Okay. So more stuff. If you then go back here, you will see that there are different channels. Oops, not that one, but that one. So in the doc folder here, this is also where you find essentially all the teaching material. So you will find files of the projects, different programs. In the pub folder, if you scroll down, you will also find all the weekly information. So if you don't like a Python, a Jupyter Notebook, which is the one I use by default, you can look up the PDF variant. Or if you prefer an HTML, you can look up that one. However, for display and running of codes, I will essentially, in the lectures, use the Jupyter Notebook. But you will find all the material there if you want to go straight into that one and you want to have that on your laptop. Now, keep in mind that it's up to you to use my lecture notes as a basis for your electronic lectures. So you can take everything I have and use it as you want, okay? I don't have any problems with that. This is lecture material which is available to everybody. So I take quite some pride in that. But sometimes once I got an email from a student in Mauritius, I even had to look up the place. It's an island north of Madagascar. And that person had come across these lectures and just wanted to know how to cite them. So feel free to use this, modify them, add things to them, just use them as a starting point or whatever you want. Okay, so that was that. What else? I'm going to do one small thing here. I'm going to, sometimes I switch to the PDF file because there are some kind of general messages which I just want to convey. So let me just stay with the PDF for some moments before we move over to the Jupyter Notebook. Any questions about practicalities and so on? Okay, so some of the slides are slides which I will go through quickly. You've probably seen these already. You are here, so you know that the lectures is today. When it comes to the exercises and the labs, so in this course, there are no exam. There's only project work. And we do spend a lot of time on the feedback to the projects. We also have weekly exercises, which, and there will be 10 of them. And each one of them gives you an additional point to the final score. So if after the 3 projects, you have a final score of, let's say, 82, which corresponds to a B, 82 out of 100, and you've done all the 10 weekly exercises, then you get an additional 10 points. So which means you end up with 92 points, which is then an A. So the weekly exercises are also important. I mean, we want to advocate being at the lab because that's where things happen. That's where you discuss with us. We have an excellent team of teaching assistants. Those are marvelous folks. And these discussions actually, these are the essential ones for developing your intuition, understanding, and insights about the methods we are going to discuss. So the lab sessions are typically set up like 4 hours for each group, but you can, if there is space, you can actually shift between groups. And you can also stay, if it doesn't fit properly, let's say 2 hours in one session and 2 hours in the next session. You don't get booted out if there is place, okay? And some people are there all the time because they like it so much that they come both days. That's also possible, yeah. So the exercises, the place for the exercise and the projects is actually room 434. Okay. So just up one floor. No. The way we have made the exercises is that you can reuse everything in the projects. So it's a way to baby step you through the essential things, elements you need in the projects. And there's one reason for that, because you typically have 4 to 5 weeks for each project. And some of you, if you're like me, who loves procrastination, I am a procrastinator. I believe in procrastination. That's often when I have my best ideas. But it can be stressing, especially if they're 2 days before the deadline. So doing the weekly exercises gives you an additional score, but at the same time, the exercises are tailored to the projects. So you can plug in element after element, and then you will have, if you've done all the exercises, you have a good amount of what enters the project from a computational point of view. Does that sound okay? So the exercises are tailored to the project so that you actually, in a way, we are forcing you to have a kind of continuous effort and not be like me, who every time I'm approaching the deadline, I keep telling myself, Morten, why didn't you start earlier? Why do you keep repeating the same stupid errors all the time? In a way, we are humans, so we tend to not learn from our errors. Okay? Anyway, so some of the information is already, you've seen that one. I'm not going to repeat everything, but it's just here for the, we have communications via Canvas, free compulsory project. And what we normally do in the final one is that since many of you are coming from different departments, you have different data sets. So like in the first project, we are going to produce what we normally call a vanilla data set. So a vanilla data set is a thing where you just generate some simple data set, like a polynomial of third order. And then you want to fit a function to reproduce that. And this is something you can repeat again and again. But many of you do have data from your own research, from your master thesis topics, or you have some fun data you always wanted to play around with. So the final project is something where we will propose some projects, and one which has been very popular is to solve partial differential equations with neural networks and machine learning methods, which is a research field for many of you. But then you have other people who have a classification problem and want to study that with specific methods, etc., etc. So you should feel free then to think of projects for the final one, of topics. And this is something which every year, we've had then people presenting these projects to all the other ones. And then you could have an example of where people say, I like that topic. Can I join you? So groups are not permanent. If you want to change groups because you find some people are interested in other topics, after some time, that's fully possible. As I said, the optimal size for the groups is between 2 to 3 people. But we've had groups of 4 or 5 people as well. So we once had a very good group, and some of the final projects, sometimes they end up in scientific publications. So we had a group from geoscience, which consisted of one from geoscience who had data on oil wells, and then a person from computer science or informatics who knew about the algorithms and how to read the data and transform that for a specific machine learning method. Then there was a mathematician, and then there was another person whom I don't remember where that person came from, but that group actually ended up in writing a scientific article. So this can happen. There are still, in this field, there are still low-hanging fruits, in the sense that there are fields which are still lagging a little bit behind with the introduction of deep learning methods. So this is a team of folks, and we will normally, on average, try to be 2 at every session. So we have slots from 8 to 10, 10 to 12. So there will always be 2 of us. Now, one thing which I tend to do sometimes in the first hour of every group is to, and some of these things are recorded, is actually to go through technicalities relevant for the exercises which we are solving. So there may be some additional theory which we didn't have time to cover in the lecture, which I sneak in let's say in the first 30 minutes. And we also want these labs to function as a kind of flexible learning environment where we sometimes take a break and we ask questions to you. What does it mean? What you're doing? So that's a way to actually break the monotony where you just sit there and strive for 4 hours, consecutive hours, and then just having some questions from us breaks often the monotony. Also, if you're interested after you've gone through this course, and if you want to be a TA next year, just shoot me an email. So we, as you know, I mean, the TAs are central for any course. This is about the rules of the game and when we are going to propose projects. So these deadlines are tentative. So tentative means for somebody like me, who is a notorious procrastinator, this means that we have always some flexibility to tweak them. But they are there for your planning of the semester, okay? So you know exactly when we are expecting things to happen. So sometimes it happens that somebody gets ill, then you just send us a message and we could give you an extension. If it's more than a week, then typically you would have to hand in a documentation from your doctor to the study administration. But often, if things are going wrong towards, let's say, the deadline, please let us know ahead of time. And as you see, you have these extra credits. So it's not mandatory to do these exercises, but it gives you an extra credit. And this is the final, the score list. So clearly, if you have 82 and you've done all the 10 exercises, then you get 82 plus 10, which gives you an A. So we try to stick to this table, but there's always some flexibility. So that it's important that the rules of the game are set so that there is no surprise. Okay. Any questions so far? Yeah. So I just have to get closer because when I have these ones for the people online, then my hearing is actually getting bad. Yeah.
Is there a weekly assignment this week?
So this week there's a weekly assignment, but it doesn't count for the final score because this is just installing software and so on, but you can upload them. And the feedback which we give you is it's a kind of quasi feedback. It's nice work, well done, keep on. So it's only for the projects that we give you a detailed feedback. So next week, the weekly exercises count 1 point each. This week is just a warm-up, just to see that everybody's on the same pace. And if you want to jump into next week's exercises, feel free to do that. Because, I mean, as I said, you guys are going to be a pretty heterogeneous group with people coming from essentially all departments at the College of Natural Science and also from other colleges like medicine or whatever. Yeah, you've seen this. So one question to you all guys, how many of you, yeah? Could you say it again? So as I said, for the assignments to get approved, is that what you're asking for? Or the coding? So could you say? Not for the weekly assignments. Maybe I didn't hear properly here because I might actually, yeah. Okay, so there is a way we grade the projects, which is on the website of the course. So let me show you that one. So let's just do that. And then we switch a little bit. There's a question to you online on what are the criteria for the projects. So if we now go back and go to the GitHub address of the course, and then you go to the doc folder and go to the project folder, you will then see evaluation and grading. So that's And there you will find the criteria for how we grade in order to get, let's say, 100% score. There are some examples of previous projects which we're going to update. So this is a good question, actually, because if you look into the way we want you to write the projects, and this is something we are going to discuss during the lab sessions. Actually, one of the weekly exercises is about writing the abstract, the introduction, and a reference list for the first project. So you will see that we want you to write these as a scientific article. So the exercises or the projects are not going to be like answer exercise A, B, C, D, but we want you to write everything like a scientific article, because that gives you a training when you're going to write your master thesis. So how many of you have written a scientific report? Okay, well, it's a good fraction of you. So you know that there is an abstract, there is an introduction, there is a theory part, methods part, you describe your code, results, conclusions, appendices, etc. Yeah? No. So the weekly assignments are more like A, B, C, D, and you just answer the different questions. Yeah. Now, the main reason is that many of you who have not written a report, you will see that the templates for these reports really look like your master thesis or any scientific or technical report. So when you get a job, you will end up writing technical reports or reports in one form or the other. And they're going to have the same layout, whether you're doing a report for, let's say, a company, or you're doing a scientific research or whatever. So this is the way we actually, and you will see the score, which we typically give. And when we grade these things, it's always 2 of us on each, and we always change who grades whom. Did that answer your question? So you can find all the information here. So let me go back to the slides. So we're going to use 2 textbooks, and I'm going to send a weekly mail with the plans for the specific week, and then you will see the links to literature. And one book which I'm going to use is the one by Goodfellow et al. So these are some of the world-leading experts on machine learning and deep learning. You can access that for free. The same applies to the textbook by Sebastian Raschka. So that has lots of Python code which you can use, etc., etc. You can download that for free. Are you familiar with how you download things at the university? So at the university library, we actually do pay for many of the books, which you can download free, the electronic version of the textbook. So the textbook by Raschka, if you follow that link and you log in at the university library, you can actually download it for free and have it on your laptops or tablets or whatever. Okay? So there are some other textbooks which we will also use now and then. Actually, this one by Jeroen is a pretty good one. This is a classic textbook, and you will also find these in different formats at the university library. So this week, we are going to have a quick refresh of linear algebra, and I typically recommend taking a look at Goodfellow et al. Chapter 2, and also you're going to install scikit-learn and Python libraries. And yeah, I'm going to skip some of these slides here, but I wanted to say a little bit before we take a break about the main parts of the course. So there's going to be one part which is statistics, and then we have the machine learning methods. And these methods, the way we are going to teach them is actually to present them when we need them. That means also that some of the mathematics, sometimes we will just state the theorem and use the theorem with the algorithm. Other times we may go into more details of the mathematics, but in general, when it comes to, let's say, a theorem like the singular value decomposition, Are you familiar with that? Do you remember singular value? SVD is the most beautiful algorithm in linear algebra. So if you haven't seen it, you can look it up. It's my favorite algorithm. You can do everything you want with a matrix with the SVD. And this is actually something we often use to analyze data in the beginning. So statistics also plays an important role when we analyze data, although in this course, there is an emphasis on what we, from a statistical point of view, call a frequentist approach. Does that say anything to you guys? So who has heard of frequentist and Bayesian statistics? One, yeah, someone, excellent. So frequentist approach means practically that we take a data set, and this is the case, the standard case in machine learning, and we are interested in fitting a model to reproduce the data. That fit is going to be used to make predictions. But we are not interested in a probability distribution. So when you take a Bayesian approach, in essence, what you end up doing is to obtain or make a model for a probability distribution, which then can be used to generate new data. But at the same time, when you have a probability distribution, you can ask for more. Because when you have a probability distribution, you can ask, what is the likelihood of B given A? You can start looking at causality, but you can also determine the error on the parameters which make your model. When you do a frequentist approach, this is less common and it's a little bit more laborious to define a probability distribution. So we will often in this course follow that path, but I'm going to mix in some statistics here and there. Now, one of the problems with many of the bachelor programs we have is that when we shape them, we often thought that in the beginning that statistics is something you can pick up on the way. An element here, an element there. This never works properly because you don't get a coherent exposition to statistics. So many bachelor programs now are reintroducing a full semester statistics course. So how many of you have taken a full semester course in statistics, elementary? Excellent. I'm going to repeat some of these elements, but you will see that the course is a mix of statistics and linear algebra. So I'm going to skip some of the slides here, but basically what we will cover some basic concepts, and we will remind you of some simpler things, some central aspects on Bayes' theorem. So Bayes' theorem is a very simple theorem to develop, and it plays the same role in statistics as Pythagoras in geometry. So Bayes' theorem is an essential theorem, and we are going to look at variance because when we look at linear regression and this classical regression method, you can actually derive all the equations from a statistical point of view. And that is actually what Gauss did. So linear regression is normally phrased as a plain linear algebra optimization problem, but you can actually take a Gaussian distribution and derive the same equations. So Gauss is one of these people which are intimidating because when you do computational science, the name of Gauss pops up everywhere. And you have a kind of feeling that these people did everything. What is left for us to do? There is some place for us as well. But Gauss, what Gauss contributed to in science, especially mathematics, is just amazing. Another thing which we will look at, and you will encounter this already in project one, that is optimization and gradient methods. So that's a central part of all of machine learning, which many people are not aware of, but it's actually at the heart of every method. You're optimizing a function, which means finding either the minima or the maxima of something. And we will see that after the break. Yeah, and then we have the pre-deep learning methods. So we will normally deal with linear regression. These are the classical problems, decision trees, and some support vector machines. If we get time, we will say something about unsupervised learning. And then we have the deep learning methods, and we will essentially focus on these three. And then we have advanced courses, which actually cover some of these other methods. So there's one thing I wanted to say here before we move on. So there's a list of courses at university which offer courses on machine learning. I'm going to skip some of these, but I wanted to say something about generative methods and discriminative methods. So how many of you have heard of generative methods and discriminative methods? Ah, it's a good fraction. Excellent. It's actually getting better and better year by year. So generative methods are something which we will cover less in this course. We will focus very much on fitting a function to some data, which means that we will often deal with what is called supervised learning. So supervised learning is expensive in the sense of getting the data, because you have data which are labeled. So a label means that you have classified the data, whether that is a Van Gogh painting, whether that's a horse or cat. So it means often that there is a human who has done the classification for you. Then a generative model is actually where we have most of the modern methods, or the interesting methods, where you actually train data to make a probability distribution. And then with that one, you can generate new data. So you can train on horses, and then you can, everybody here has probably used the image making in ChatGPT. Who hasn't done it? Stupid question. Okay, should try it. Actually pretty good. So 10 years ago, these algorithms and the program and the access to high performance computing facilities, which could train a model, was so and so. So when you then ask the program to generate a horse, it could come a horse with 2 heads and 10 legs or whatever. But nowadays you get pretty good images. Actually, ChatGPT and these kind of tools is something we strongly recommend that you use. We are coming back to that. It's a fantastic tool for debugging, for instance. It's also a fantastic tool for learning to program properly, because it often gives you many hints. So when you write a program, if you write your own program and then you can ask ChatGPT, can you improve the program which I've written? The improvements are often really good. But the important thing then is that you know what you're doing, because ChatGPT can make errors. And we've seen that. But this is a tool which we are going to discuss a little bit during the labs. And we normally recommend using them, especially when you write your reports, because many of you, most of you, are not English native speakers. So it's also a way to learn to write a good English, if it's used properly. So we are coming back to how to use it. But in essence, is the strong recommendation of using all possible tools for doing science. So generative methods means simply that you have produced, in essence, a probability distribution. If you look at what we are going to do, to a large extent here, in this course, since this is a building stone towards more advanced courses, is actually to focus on discriminative methods. So a classification problem like this one is where you train on images, in this case, paintings of Van Gogh, and then you put a label, yes, no, or 0, 1. And then you train a model to recognize Van Gogh paintings. And then your model will then say something about whether this is a Van Gogh or not when you feed it with a new painting. This is a classical example of a discriminative model, which is the type of modeling which we will stay with. So we will essentially stay with supervised data, labeled data, but we will also look at the unsupervised models. So a neural network can actually be used as a generative model, although it normally falls within the slot of discriminative model, because you can use a neural network to solve a partial differential equation. And in some cases, these solutions can be interpreted as probabilities. So I'm going quickly through some of these things, but I'm going to skip some of the slides here. And right now, before we take a break, I wanted to go back to the Jupyter notebook. not that one, but this one. So there's a lot of blah, blah in the beginning here, and you can revisit that one in peace. But the thing I wanted to point to before we begin, we take a small break, is about the, not about what's a good model and so on. So in the lab session, we will discuss this, but there are some Python soft libraries, which we strongly recommend for this course. And I will say something about some of them. So how many of you have used Pandas? Excellent. So keep using it. There's also Pandas AI. Have you tested that one? Anyone? Right. It's pretty good. But then, since I said that there is an optimization problem, there is a library which previously was called AutoGrad, but now has been replaced by JAX, which also contains just-in-time compilation. But AutoGrad, which was merged into JAX, contains one of my favorite algorithms, automatic differentiation. It's the closest you get to painless dentistry, whatever that is. It takes away all the pain with calculating manually derivatives. Because when you've calculated derivative once or twice, you don't get a deeper insight about the mathematics. It's okay to calculate by hand, but often when you have written a program, you would try different functions. So automatic differentiation is not numerical differentiation where you take finite differences. It's not you calling symbolic Python or Mathematica to find the analytical expression. It's actually an operation on known functions like sines, exponentials, etc., where you calculate the derivatives to machine precision. And it means that you can then change, because when you set up a code for a neural network, you're going to try different types of so-called activation functions. And it's pretty boring and easy to make errors when you're calculating many derivatives by hand. Just ask me. I've done so many stupid errors through my life by simply forgetting a constant or interchanging two indices and so on. And then you spend a week to find the error. So automatic differentiation is a tool. If you haven't used it before, use it. And we are going to actually discuss it a little bit later. You will actually encounter this already in project 1, in the optimization part and gradient descent. Okay, went a little bit over time. So after the break, we are going to remind ourselves about the linear regression and some of the basic mathematics which we need in order to get started. And you probably have tons of questions. Feel free to come in during the break, ask questions. When you ask questions in the audience, please keep in mind that I have these AirPods here, and sometimes I don't hear well. I also don't hear well in general because I've been having too much music going in here, which has ruined my hearing, obviously. Let's do 15 minutes. Is that okay? 15 minutes? So for those of you online, we take a small break. So what I wanted to do now is to go through some of the technicalities behind linear regression and also set the scene for the basic overarching approach, which we need to take when we are looking at a machine learning algorithm, whether this is deep learning or some of the simpler ones like linear regression. But before we do that, I just wanted quickly to remind you of what you find online here. So there is a repetition on how to use NumPy. Who has never used NumPy before? Okay, so we will do that at the lab. We can discuss that. And you will find ways by which you can deal with standard vectors and matrices. So this course, if you think of a deep learning method like a neural network, at the bottom, it's actually a set of matrix and matrix vector multiplications, which you end up doing, together with applications of the chain rule, like this automatic differentiation. So NumPy is going to be one of these essential tools which we will encounter again and again. And it's a library, an efficient library for dealing with matrices and vectors and higher order matrices, which are tensors. Okay, so I won't say so much about some of these libraries because I wanted to dive into more the basic aspects of linear regressions. But we are going to encounter TensorFlow, which was released by Google in 2015, and that is their deep learning library. And then we have PyTorch, and the textbook by Rashka uses PyTorch. And many people prefer using PyTorch because it allows you to program in a more Python-like way, in an easier way. But we are going to show you how you can use both libraries, both PyTorch and Keras, and you will find examples when we come to deep learning. Project number 2 is actually going to be you writing your own code for a neural network. And that is very useful because a neural network is the basic building stone in all of the deep learning methods, the familiar ones, like convolutional networks, autoencoders, etc., etc. So having written a code for a neural network is something which we think is a good pedagogical exercise to just demystify what happens. And clearly, if you want to use R, you can do that. You know that Jupyter stands for Julia, Python, and R. That's the 3 languages. So you can open up a window in a Jupyter Notebook where you can write in Julia or you can write in R. But normally we recommend using Python because the big community is actually using Python here. So there are things here which we will discuss more at the lab sessions. And I'm not going to discuss these NumPy, the basics, because many of you have already seen that. So these are also things which we will discuss more during the lab sessions. So these are technicalities. So I hope you can forgive me, even though it's in the weekly material, there is material which we discuss in the lab session. And this is a typical technicality. So one thing which I also recommend you to take a look at is actually pandas, just to remind yourself a little bit about that. So here's about matrices, etc. Pandas is an extremely useful tool, which many of you have encountered. And you will find examples in here. You can see now what kind of movies I like. So this is a kind of generational problem. So if you hear me cracking jokes from the Lord of the Rings, and you understand where some of my favorite movies are from. So how many of you have seen those movies? Well, basically, I can crack some of my lame jokes, right? So like you're going to write one program to rule them all. So once I actually was teaching a course on mechanics, and I said that you're going to write a program which is going to rule everything you do here. And this guy was totally addicted to the movies. And he showed me, took off his t-shirt, and he had a Balrog tattooed on his back. So if you haven't seen the movies, it doesn't say anything to it. Anyway, so these are just some simple examples, which I'm not going, but it's actually a very useful tool when you're reading in data from files. So I strongly recommend using pandas because it allows you to organize the data in a quick way. And I'm going to show you an example from a data set which has been produced for labeling nuclei and their energies. So this is a data set with something like 40 columns. And I once met a student who spent 2 months to write a program in Fortran to read that file. And you can do that in 2-3 lines with pandas. I just wanted to show you an example which is very powerful, very quickly. So many of you are familiar with this, and you see you can, I really like this, you can immediately change this into a data frame with a data frame. And you can, so if you just print this one when you take display, then you have quickly a matrix. So the data frame gives you typically a matrix, and you will often end up working with matrices. And you can keep adding things. So you can have, you can easily append data here, and you hub it, and then you keep adding. But the example which I wanted to show you, one example is simply you setting up a matrix, and you can then set up a matrix of 10 times 5. You're filling it with random numbers. You define now an object, which is this data frame, and then you display it. You can calculate the mean of each column, and you can calculate the standard deviation of each column. You can square the elements, etc., etc. So you can actually do lots of mathematical operations. And the thing which is very useful here, like when you calculate the mean, so this is the mean value of every column. We are coming back to this because in many models, in many of the machine learning algorithms, we are going to pre-process the data. Pre-process means to make the data better tailored to a specific algorithm. So one thing, what that often means is to subtract the mean value in each column, because that can reduce the effect on outliers in your data set when you make the fit. So calculating the mean in this expedient way for each element, each column, is a tool which is very useful because it's just one line. And to write your own code for doing the same thing is okay, but when you have pandas doing that, it's much more efficient for you from a programming point of view. So it's okay to write things from scratch, but then at a certain point, when you have understood what it means, using these libraries, which often are highly tuned for vectorization, even parallelization, is something which we always recommend to use. And pandas is actually a very useful way of doing these things. So you can calculate the standard deviation, you can perform mathematics here, you can, like in this case here, you can now make a plot, first, second, oh, here I did something, I actually forgot to run a code. It's not so important. If you run it, it should come there. But I wanted to show you an example here of how you use pandas on a data set, which is a little bit more complicated. So let me just bring this up. We are coming back to this in the exercise sessions. So this is a data set where you calculate the mass excess of a nuclei. And the mass excess is an experimental quantity. And there is a table or data which is being produced every 4 years. It's actually the latest one is 21, I think. I haven't updated it. It's not so important here. But if you look into the data set, so if you now take a look at the file, so let's just go to the place where we have the data file. So the data file looks like this. So there's a lot of text in the beginning, and then you have columns with data. And you have to identify the right column. This is also a formatted output with an old dusty Fortran deck, which has been used to produce the data. And it contains a number of nucleons, which is neutrons and protons, and the different physics information about decays and so on. So this is something which you can read easily with pandas. So let me show you how you can actually read that table and simply use this information in this column, the Z and the A information. So if you then scroll down, we are going to make a fit of a model, which runs like that. So you have to forgive me a little bit for bringing in a physics case, but this is just an example which I bring up because it shows you how you can use existing software to read data from a file, as long as you know what the file means, and then set up an array with the data and then make a fit. So when we have discussed this, we are going to go to the mathematics of what is going on. So we are making a fit of a polynomial. And this A is the sum of neutrons and protons. This is just an example data set, which goes beyond a simple vanilla data set. So in this particular case, what you have now is a parameterization where you can fit a polynomial which doesn't go like x squared, x cubed, and so on, but has different powers. But you can feed that into the model, and you can do linear regression and make a fit. But pandas is in this case extremely powerful. So here I'm just reading the data and I'm sorting everything out and I'm setting up everything so that I set up files and so on. So this here decides which columns you want to read, 2, 3, 4, 6, and 11. These are the columns. And you assign a label to them, neutrons, protons, sum of neutrons, protons, the element name, and the energy which you want to fit. Here you have to be a little bit more specific because pandas here reads a formatted file. So this F stands for a file which has been formatted in a specific way. So Fortran could actually give you very detailed ways of formatting the output. But then you see now that you can take the data of these energies and you can then define a numeric error. You can drop cases where you don't have a number. Drop NA is an extreme. You will actually see one thing you always have to do when you're dealing with a data file is to look at the data file if you can. Because in many cases, there can actually be wrongly typed entries. So typically an entry which is labeled by a human, suppose you're having a table of, let's say, credit card debt, which is being respected or not. So that's a typical classification problem, yes, no, a binary problem. And then typically you would put 0 for somebody who pays the credit card debt, and 1 if you don't pay. But sometimes if you look into the table, you will see that the human who has punched in 0 and 1 sometimes punches in 2 or 3. So this happens. So to look through, if you can, always look through the data set. So drop NA means that sometimes there is not an entry. So NA, not a number. So you just skip that and you don't include it. Sometimes you would actually replace that one with a prediction you make. That's also possible. Or you could take the average value of a set of measurements. But many people prefer to drop if there is no data. Then you can just divide by 1,000 if you want to have a more convenient. And then you can group them. This is an extremely useful thing because now you have 1, 2, 3, 4, 5 columns. And now I want binding as a function of A. And then you just group by A. And then I'm just interested in the maximum values because I have many different nuclei. I do that. And now you can see a typical array, which looks like this. So I have 270 something. And these are just names of the elements, etc. So I'm sorry for those of you who are not from physics, but I just wanted to show you how you can efficiently read data with pandas. So if in project 3, you're defining your own data, using data, actually handling the data, which is something we are a little bit sloppy with in this course, that can actually be 80% of the task. So most of the data sets which we are going to deal with are data sets which are well-defined. So we don't need to worry like that. But the data sets which you may encounter in your master thesis or your PhD research can be data sets where you really have to go into it and see if there are things which are wrongly entered. So we had, I'm saying this because it's a boring thing, but it can make you waste tons of time. So we had a master student once who was making a weather model. And the unfortunate thing was that the wind speed, one year was in meters per second. The next year was in kilometer per hour. So different entries, different years were registered in a different way. And when you are fitting meters per second towards against kilometer per hour, you just get a model which didn't make sense. So that's a typical case where you can get lost. So the data set itself, we're not going to worry that much here. But in project 3, in case you're using data sets which is not really trimmed to the specific task, then you may have to be a little bit careful. Just a small warning. But now we need to introduce different things here. So I am mentioning something I call a design matrix. In this case here, I'm actually fitting a matrix with a polynomial of different degrees. So this is going to be my model. And I use scikit-learn, which is a very popular library, which you will need to install and compare your own codes with. So that makes life very easy. So you can see I do linear regression, fit. This is the input, this is the output. And then I make a prediction. And then I calculate something which is called the mean squared error. So let me just redo that one. So this is using scikit-learn. And I'm going to demystify this now. And this is what you get. You get a mean squared error, which is 2 times 10 to the minus 2, which is not so bad. And this is the comparison between your fit and the data. So the blue line is the data, and the pinkish one is your fit with a polynomial fit. So let's try to see what this actually means, okay? What have we done here? So how many of you remember linear regression from linear algebra? It was pretty good. Do you get offended, those of you remember, if I remind you of what it is? Is it okay if I just go through? And for those who haven't seen it, I'm going to try to baby step you through the details, okay? So I'm going to stop here with the slides. And I want now to switch to the whiteboard. Let's do that. So one thing which you will also have access to are the handwritten notes. So this is my variant of the Blackboard. I won't use the Blackboard, I will mainly use the whiteboard because those online can see it, but also I'm going to upload the file here after the lecture. So you also have that for your records. So essentially what we are going to do is the following. This is the main picture. So we are going to have, if you look at graphically what we're going to do, we are going to have some input. Okay. And I'm going to call the inputs for x's. So this can be a single value, or it can be a vector, or it can be a matrix, or it can be a higher order matrix, which is a tensor. Okay. But now I'm going to just leave it like this. And I will, from the text and the context, you will understand whether this is a vector or not, okay? And if I put subscripts on everything, then it's obviously an element of either matrix or vector. Now, this is the input. And then this is going to be fed into a box here, which is going to be my model. This model is going to be a function which I'm going to make up. And this will be a function of parameters, theta. So there's going to be a set of parameters. And this is the optimization problem. So we're going to use this as an input to an optimization problem. So what I'm setting up here is totally generic for all of machine learning methods, which we are going to meet. Now, this produces an output, which I'm going to call y tilde. This is the output of the model. It can be a vector, or it can just be a scalar or a matrix. Now, this then is fed into a function here. So this is another box, which I'm going to call, so the y tilde is the output of the model. So this function, which you see here, is normally called the cost or loss function. And you will see me using cost function for the main object, which is the sum of all the small so-called losses. So loss in this sense, because we are going to use as a way to gauge the quality of the model, the mean squared error. I'm going to remind you what the mean squared error means. So this is going to be a function of y tilde, which then is a function of theta. And then it's going to be the function of the data. So in here, we are also going to feed the output. This is also called the target value. It has many different names depending on the literature you're going into. If you go to finance, this cost function is often called the risk function. I often like to call it the error function because in many cases you define some kind of standard error. So this function, which is this y here, that is my output. So the thing now is that these two here in red, these are our data. And essentially all of machine learning is actually about finding a model which reproduces your data. This cost function is a way to gauge the quality of your model. So one of the simplest of these functions is the mean squared error. So let's just write it down here. Mean squared error. So this funny letter here, which you see, that is my attempt at making the letter R. I hope you can live with that. So the mean square error means that we are going to have a function of y and y tilde. And now I'm going to make an assumption. So I'm assuming that y is a vector which contains real numbers and n entries. That obviously means that y tilde is also a vector with n values. So to remind you a little bit of a vector here, this is the transpose. That is now going to be given by y0, y1, up to some y n minus 1. And the same with y tilde. And this says y0, y1, 0, and all the way up to the final value n minus 1. So this is the model output and the data, the output data. So this could be the result of a measurement which you're making. Suppose you are measuring the amount of, let's say the velocity as a function of time. So time would be your x value, and y would be the velocity which you measure at a given time. Does that sound okay? So the mean square error then is then defined as 1 over n, the number of data. So it's a sample mean value. This is a definition. So it clearly tells you that it amplifies large differences. So when you make a model and you have some large differences between the model and the data, then clearly the mean squared error amplifies that because it squares that. So this is just one of many ways of assessing whether the model is a good one or not. So if you have a mean squared error 0, it means you have a perfect fit. Okay, so this is just one of the many possibilities of cost function which you are going to encounter. And this is one of the simplest ones. And it's called an expectation value because you have a sample. And when you sum over all the differences and divide by the number of values, this is called the sample mean value. If you knew the probability of that, you could calculate the exact mean value. But we will always be stuck with a given amount of data. Except for the simple examples which we are going to look at the beginning, where we are going to generate as much data as we want easily. But if you're running an experiment, like there was a big one in the UK, where they surveyed 500,000 people for 30 years, for heart disease and all the kind of factors which could influence different types of heart diseases. This is the type of experiment which you will not be able to repeat. The data that you have then is the data you have. If you run an experiment at CERN, so CERN has a electricity bill, which is bigger than the city of Geneva. And an experiment runs for half a year, which means that it's very unlikely, unless you can claim a Nobel Prize, that you will be able to rerun the experiment. So the data you will have is the data you have. But except for us, in the beginning of this course, we are going to be able to regenerate the data again and again. So we don't worry about that. So we can generate as much as we want. But this is the function which we are going to optimize. So the optimization problem, which we are looking at now. Oops. So the optimization part that is us taking this function as a function of the parameters theta, and we want to drive that to 0. That's the optimization. So theta can be a scalar, but it could also be a set of parameters. So a typical example could now be you having some data set. So suppose you have X and Y, and you make a model. So your model then, to model this Y, is to make an approximation. And then you let your Y be given by some parameter alpha plus some parameter beta multiplied with X, just a linear fit. And if your data is generated by a straight line, then you would probably be able to reproduce this perfectly. And you will find an alpha and beta when you minimize the problem, which gives you a perfect mean squared error. So in this specific case, what we are doing then is to make a polynomial to first order. So anyone remember what we typically call this line? No, this point, alpha? It has a name in the literature. Yeah, the intercept. So this is the intercept. And many of these models often subtract the intercept in the fitting, because then you have a less bias on the intercept, which can be a large value sometimes. So this is where you cross the y-axis. What would you call beta? Yeah, the gradient or the slope. That's the Norwegian stigningstall. So that means that in our case, theta contains alpha and beta. So that's 2 parameters. Okay? So that means that my theta, if I look at this one, theta is going to be a vector of length 2. So I would write theta in the following way: alpha and beta. So what I'm going to search for is the derivative of C with respect to alpha and the derivative of C with respect to beta equal to 0. This is my optimization. And this is what is at the heart of all of machine learning. The nice thing with the mean squared error is that we get an analytical expression for the parameters theta. So I'm going to set in a new equation, which you will see again and again. So if I put a hat on theta, this is what we are going to call the optimal value. And that is the one which takes the argument and minimizes this function C of y and y tilde for theta elements in R, and we have P parameters. In this case here, this P is equal to 2. Okay? Any questions? It's too simple, or is it okay, the pace? Yeah. So I just want to have you with me with the overarching things which we are going to do here, and the namings which we are going to use again and again and again. So when you see a parameter with a hat on, that is my optimal value, which follows from the minimization of the mean squared error. Now, something which we will see a little bit later is that the mean squared error gives us a convex function. So we are going to show that. And when you have a convex function, it's a minimization problem. If you have a concave function, it's a maximization problem. So you can always choose whether you want to minimize or maximize. And if you have a maximization problem, you can put a minus sign in front of it, and then you have a minimization problem. So convex optimization is an art by itself, and it's a field by itself. And if you want to dive into the beauty of that mathematics, we do have courses in the Department of Mathematics on optimization theory. So we are going to look at many simpler examples, but the essence of what you're going to see throughout all these lectures is actually expressed in this image here. So you have some input data, you make a model, then you want to assess the quality of the model by grinding through the output through some function which you have defined. So when we come to classification, where we have binary outputs like 0 and 1, true, false, etc., then the mean squared error is not the best way of doing that, because the mean squared error will favor a continuous function which is being fit. And that's not what you want if you're doing a classification with discrete outputs 0 and 1. Then you would like to fit a probability which gives you 0 if the value is below a threshold and 1 if it's above a threshold. So the kind of function you're optimizing depends on the data set. But the mean squared error is, in a way, intuitive because it tells you that if you make a crappy model with large deviations, they will be amplified because they are squared. Now, there's one thing which I would like to ask you. We are going to see the answer a little bit later. I could have taken the absolute value and not the square, right? If you now look at the optimization problem, so I could have replaced everything with a function which goes like y minus y tilde. What we are doing is this. This is the optimization problem. So, and many people use actually that function. You're going to encounter that one. From the mathematics, could you say something about what could be more beneficial if you do the mean squared error compared with the absolute value? Yeah. Yes. So we are going to get, with the mean squared error, we are going to get an analytical expression for the parameters theta. When you take the absolute value, you won't get that. You can still do it numerically. And we are going to see that later in project number 1, where you're going to program a method where you have to take into account the discontinuity. So when you take the derivative of an absolute value, that gives you a discontinuity, because let me just sneak that in here so that you see that. So if I take d of x with respect to x, that is +1 when x is larger than 0, -1 when x is smaller than 0, and then you have a discontinuity at 0. So many people are sloppy and they just put that to 0. But mathematically, that's a little bit cheating. There are many cheats numerically, actually. Many cheats. And we are coming back to some of them. Like when you want to invert a matrix and you have zeros along the diagonal, you can actually add a small number and then you can invert. That was the way the divergency in the mean squared error method was handled in the beginning. And we are coming back to that. So let's continue a little bit now, because if we look at this simple model here with alpha and beta, what we are going to do now is to assume that if we now look at the parameter y, there's a y0. By the way, why do you think I always begin my arrays with 0? Is there any reason for that? Why don't I start with 1? Yeah. Python and C++ programming languages, they start the arrays by default with element 0. That's why I start with 0. That's the only reason. Okay, so if you look at that one, what we have is alpha plus beta times x0. We have y1, and then alpha plus beta times x1. So this is my model now. And then I have yn minus 1, which is alpha plus beta times xn minus 1. Now, what you see here looks like the rows of a matrix multiplied with a vector. So I can define a matrix now, which you're going to see again and again. And this is one of the things you will have to set up next week. And this is called the design matrix or the feature matrix. And I'm going to call this matrix for X. And that has now ones, 1, 1, 1, 1 down here. And then it has x0, x1, down to xn minus 1. This matrix X is now a matrix of dimensionality n times 2. I have two features. They're also called predictors. So the features are now the parameters alpha and beta. So this matrix is the one which we have to set up when we are going to make a model. If we now make a polynomial fit, the features will be given by the degrees of the polynomial. If I have 100 data points, n, and I want to fit a 99th order polynomial, in order to have 2 points, you can fit a straight line, 3 points, second order polynomial, etc., etc. So if I'm stupid enough and somebody gives me a first order polynomial, and I want to fit that one with a 99th order polynomial because I have 100 points, then you would probably just get crap out. But I could actually fit this with a, if I have 100 points, with a 99th order polynomial. Then my matrix X would be 100 times 100. So the way I'm going to label things in this course is that every column, not row here, stands for the data points. So n data points could now be, suppose you're making a model for house prices. So one column could now be the number of rooms in a house. Another one could be the number of bathrooms. Another one could be the size of the property, etc. And then you have a final output, which is a price. And you want to make a polynomial where you take these features as way to make a prediction about the price. And it's pretty obvious that the price is strongly correlated with the number of rooms, the number of bathrooms, etc. Probably less correlated with the color of the house, etc. So this matrix is something which becomes essential. So this is the design matrix, and you're going to see that again and again. So if I have a 10th order polynomial, I will have 10 elements here, 10 columns. So the columns represent the feature. So coming back to this housing model, the features could then be the features of a house. Your output is a price, and you want them to make a model which predicts the price according to specific features. So that's just an example. So if you then look at what we have here, is now that this y tilde is now a vector. So remember, y tilde is a vector of dimension of length n. This matrix X is a matrix of dimension n times 2 in this case. In general, I'm going to use the letter P for the number of features. So I'm going to have something like this. And in general, they are not the same. If I'm making a polynomial fit and I have equal number of columns and rows, that matrix has a name in the literature, which is called van der Monde matrix. That's a famous matrix you may encounter in linear algebra courses. But that means that my y is now going to be given by this matrix X multiplied with this vector theta. So theta, remember now, is this vector when I take the transpose, which contains alpha and beta. Then, when I'm now setting everything in to my mean squared error, and this is the optimization part, and it's the last thing we do today. So my C of y tilde, that is given by 1 over n of y, and then I have y of I minus yi tilde squared. And when I plug in my simple model, this is 1 over n of I, of y of I minus alpha minus beta times x of I squared. That is my matrix, which has now been translated into explicit values for every row in the equation which you saw previously. So what I've done is simply to translate every row here into a more complex, into a compact matrix vector problem. And you can rewrite this now, since the mean squared error is a number. So that means it's a scalar. So what do I need mathematically to get a scalar when I'm multiplying two vectors? So just to remind you a little bit. So these are elements of a vector, yi, and these quantities here with a vector theta multiplied with these entries x. So keep in mind that the mean squared error is just a number, so scalar. So if I want to write this in a more compact way, as vectors multiplied with vectors, what should I do then mathematically? Should I take the outer product or the inner product? Do you remember the definitions of the two? Yeah? Inner product. So I would take the inner product of these two vectors. So what I would do then is that I can rewrite my quantity, y tilde. There's a 1 over n. And then I have vector y minus this x times theta, which is a new vector, transpose. I need to transpose it. That's the inner product now. Multiplied with y minus x of theta, like that. So I'm going to give you the answer now, and we stop there. And next week, we are going to go through the derivation of these quantities. This is actually one of the exercises next week. But now I want to give you the answer. So this is, this is just like this TV series, right? You see the first episode, and then you're left in a kind of suspension, and you cannot wait till the next lecture to see the follow-up, right? So what you can do now, when you take the derivative with respect, and this is an x, no, not c, but c, and this is where we stop today. As a vector, this is actually a vector because theta is a vector. When we take the derivative of that quantity, we want that to be 0. And what we will get then is the following. So let me just set it up here. And let me set it up correctly. So I multiplied away a minus sign because I actually get a -2, which I multiply away. So what I'm going to get now is something which looks like this: x transpose times y minus x times theta, and that is going to be 0. And when I fix it again, I will find that theta, the optimal value, is going to be given by the inverse of this matrix multiplied with x transpose multiplied with y. So we are going to, in the exercises next week, we are going to derive this expression. I recommend that you take the simple example, which we have here, the two-parameter case, and you take the derivative with respect to alpha and with respect to beta. And then you can see that you can generalize that to something which is going to look like this. So next week, we will go through more the mathematical details, but the expression which you see there is our first machine learning encounter. So we learn the parameter theta. This is the machine learning. We are learning theta by taking the inverse of a matrix, multiplying that with a matrix, and multiplying that with a vector. And that is our first machine learning encounter. You can derive these equations by starting by assuming that y is distributed according to a normal distribution. And you can derive exactly the same expression. And this is why linear regression, although you have seen this before in a linear algebra course, is included in the family of machine learning methods, because you have an algorithm which learns the optimal representation of your model. Then, if you have a perfect mean squared error, you have a perfect fit. If you have noise, as you will see in the exercises, you will never get a perfect fit with a polynomial. And this is where we are going to be spending lots of time on making fits to data with different models. And we don't know a priori whether our data follows a first order polynomial, a second order, or something more complicated. We don't know that. And that's the art of machine learning. So machine learning means also running many numerical experiments in order to reproduce the data. And it requires that you also have quite some insights about the data. Because if you have a good insight, then you can choose a good model. I went a little bit over time. I won't steal so much of your time, but I will try to stay within 1 or plus 2 minutes. And sometimes I give back time. Okay, Garo, thanks for coming and have a great day.